Not much of theoretical stuff is thrown in it. You just look at this familiar object or something intuitively understandable, and then you just deal with use this derivative thing. So here's implicit differentiation. So since we had that example, I'm just going to write that you did this example in the homework. X cubed plus y cubed equals 6xy. Wasn't that example, right? So this is called a Cartesian equation. Okay? Cartesian equation involves these two Cartesian coordinates x and y. And I'd like to emphasize that these are numbers, a pair of numbers, right? Two numbers. And this one is telling you about we're requiring certain relationship or condition these two numbers satisfy, right? So you're asked to pick two numbers that satisfy these two things. The focus point is in numbers. All right? And once you understand this equation and Cartesian equation, next thing they introduce in algebra course is these graphs. Graph of this equation. Not only you look at the two numbers that satisfy, you actually go to xy plane and you decide to, plot all those points. Okay? Not drawing like this. You collect one point at a time, then it kind of reveals the shape. And when you did that with the computer software, it looks like this, right? The computer images is generated out of pixels, so it's not even closer to what our understanding of a continuity and thing. It's just they just collected 10,000 and 100,000 points around it, right? But still, it has a gap in between in there. We just don't see it. So that was a collection. That's a graph, right? Still, it's a collection of two numbers, a pair of numbers, and it's visualized in there. Next thing is new, right? This thing that I'm about to write down theoretically is really heavy. It's not even introduced in a Calc 3. Most of the non-major math major students probably not even going to see it. So it's really heavy in theory, but you see this a lot, and we just wanted to intuitively approach, okay, from here. So there's this some test that you applied it here and conclude this is not the graph of a function, or is the graph of a function. Do you know that test? Vertical line test. So if you apply the vertical line test, what is the answer? Is the graph of a function, or is not a graph of a function? It's not a graph of a function. That's a global, okay? Globally, not a function. Because the graph of a function is not supposed to look like that. But what we're going to do is computing the slope of the tangent line. That's what we're going to do. Okay? So if I choose that point right there, you can think of a slope of a tangent line, right? Can you kind of picture the slope of the tangent line there? Is this positive slope or negative slope? Looks like a positive slope. When you're calculating the slope of a tangent line, do you need this piece, that piece, or that piece? No. It's just about tiny segment around it. That's all you need to compute the slope of the tangent line, correct? So we're going to sample that right there. Just that bit. That's all I need to compute the slope of the tangent line there. So I'd like to say, well, although it's globally, the whole thing is not a graph of a function, but it's locally a function. Most of the time. If I choose that point I'm showing you there, if I just take that segment, does that look like the graph of a function? If I erase everything else, just look at the red part, yes, it passes vertical line test and the graph of a function. So locally, graph function. Do you see a point in there that if you choose, little segment around it, and it's actually never going to be a graph of a function? Do you see any of that point? Yeah, intersection point seems like a little bit weird. So let's get rid of that part. So we do not see this part as a graph of a function. So do you see any other part? That's right, I think that's good. Far right edge of the here, if you choose above and below, there's going to be always intersection. You see that? There's always a twofold above it. Doesn't matter how small pieces you choose in there, there's going to be always a little one above and a little one below. It'll fail the vertical line test. So there's a few points. It's a problem, but mostly is a locally off function. Does that make sense? All right. So we don't go into any theoretical discussion here. Just to accept that, we can always assume it's a locally, the point we're looking at is a locally off function. This function is called f of x. Okay? I look at this point right there, not globally, just around that point, I have a function, right? If this graph is really representing the correct situation, I have a function. This function is called implicitly defined. Because I do not have a formula right now that f of x equals given by what, sine x, whatever, right? You just can't isolate y that easily. There is a cubic formula, one-page long formula, and then you can apply it here. But if I raise that to fifth power and fifth power, and usually there's no formula, there's no notation that we invented so that we can isolate this y, right? So, but if you look at the graph, if you understand a function in what way, I give you a number x, you go there and go above and find the y-coordinate. Does it look like an algorithm? I give you an x-coordinates here somewhere there. You go above there and read off the y-coordinate. That's your output. That's an algorithm, right? I give you an x, you do that. Therefore, it's a function. I told you even at the very beginning of the semester, that's how we define a function. But sometimes there's no formula. You understood what to do with that number, but there's no way to write down the formula. This is one of that example. Implicitly defined. We talked about it, the algorithm, but there's no expression of formula. Implicitly defined. Yet, because of this relation, we can do something about it. Right? So next part is it implicitly defined, and we write down y equals f of x here. When I write down y equals f of x, it means we entered xy plane. F of x is implicitly defined by heavy theoretical function, and not only the implicit defined, we assume those two important properties that we discussed about the function. What is the two important property that was introduced in this course? First, continuity, right? Second, differentiability. So we assume those continuity and differentiability. This is really difficult actually because you don't have a function. You yet have to discuss this property, and that's why it goes all the way to, you know, third and fourth year in math major students. You actually logically discuss this. Yes. No. Every time you see y equals f of x, that means you entered xy plane. That's what I said, right? But if you see this type of equation, it's not like y equals right-hand side everything in terms of x. If it is not like that, if it is x and y is mingled together, then you think it's implicitly defined. If y is isolated like this, it could mean many things. But if you see this, always we're looking at actually implicitly defined function, not the college algebra level of a, you know, this is xy Cartesian equation. We think about a little bit higher. All right? Okay, so we're just kind of thinking about it. We don't have a formula. We just introduce the idea, and it's called f, right? So next thing I do is I plug back in there. So where that x cubed there, and where that y is, I'm going to replace it with f of x there. And right-hand side 6 times, and where y is, I replace it with f of x. Okay? Does that make sense? So just that tiny local piece that we have this. This is no longer a Cartesian equation. This one is called the functional equation. I emphasize it here. What you're looking at in this Cartesian equation, x and y are numbers here, right? What happened? Those numbers changed to function. So if I ask you, what is this? Is not the cube of a number. What is this one here? What is the correct term? This is a function. Now before, when you look at it, I emphasize it here, that's a cube of a number. Now I'm looking at this one as what? A function, cube function. So these are all functions now. It's kind of different way of looking at the same thing, but it's interesting. And you look at a function, right? And these functions are how it's defined? Implicitly. We don't know the formula, but there is this functional equation. This function left-hand side magically turns to right-hand side function. They're identically equal. Cosine 4x equals some crazy formula. Remember that first thing we did? So that's that. So using this f of x is kind of, okay, so we still go ahead and use y and have in mind that, okay, y is a function of x. That you understand that part. Okay? So let's enter. When you look at a function and you are taking the Calc 1, and what do you want to do with that function? You want to differentiate it, right? If you have a function, and if you're taking the Calculus 1 course, you want to find the derivative of that function. That's what you want to do. So here's x cubed, y cubed equals 6xy. Don't look at it as a Cartesian equation. What kind of equation? Functional equation. What's the function? Y is a function of x. Make sense? Y is a function of x. That's what we're doing. All right. So we're differentiating with respect to what value? Function of x, right? So we're doing with respect to x. Does that make sense? We're looking at everything here is a function of x. Therefore, we're differentiating with respect to x. X cubed plus y cubed is equal to dx du 6xy. If these are numbers, differentiating it's going to be 0, but we're looking at as functions, correct? All right, so let's do this carefully. Now, left-hand side, we're not setting this one equal to each other. These are equal. If this is the same function, of course the derivative is the same, correct? So that, you see there's a 3x squared shows up in the left-hand side. 3x squared. Sum rule and power rule. And this one I'm going to write down like this and think carefully. Right-hand side, what are you going to do about that 6? Constant multiple, right? Constant multiple. So you can set outside like this. Now you look at it as x times y. This is not product of two numbers. It's a product of two functions, right? You're about to differentiate product of two functions. What rule are you using? Product rule, right? So what is the derivative of first guy? 1. And you don't touch that second one. And you don't touch the first factor and differentiate the second one. So you arrive at here. Does that make sense? Okay. So we don't know what y is. It's just an idea, so we can't do much about dyx, dy dx. It leaves like that. But we can do a little bit more about this guy. Now, we differentiate. This answer is not 3y squared. Think about it, d dx with a u cubed. What rule is that? If you see d dx and a u cubed, what rule do you apply? What's that? Composition, chain rule. That's right. I'm looking at x in there. It's not x to the third. It's something else to the third. What rule do you apply? Chain rule. Right? How does the chain rule go? I want you to look at this as a d dx of u cubed. Same thing. Remember the chain rule? So this is a 3u squared. Is that right? 3 in the, what you multiply what? Du dx. Isn't that the chain rule? Right? 3u squared times du dx. That's the chain rule. But here is y. Just another letter. You do the same thing. So how does it go? 3y squared. We differentiate, right? Times dy dx. Derivative of u. Here is y. So dy dx. We don't know what y is, but this one changed the shape a little bit to dy dx times 3y squared. We don't know what y is, but there's slightly different shape. Make sense? Next thing they do is that we wanted to calculate dy dx. Was that right? That's our goal, what the dy dx is. So it gives you some information. Still implicit, but it's better information than nothing. All right, so let me write that down. Left-hand side looks like 3x squared, 3y squared dy dx equals 6y times 6x dy dx. All right? And what was our goal? Computing the derivative, right? Which is denoted by dy dx. So I'm going to look at the term that has dy dx in it. This one has dy dx. That one has dy dx. Is that right? Everything else does not have dy dx. So I'm going to collect those in the left-hand side. So we're going to collect all the thing that has dy dx in it. Does that make sense? Everything that does not have dy dx goes to the right-hand side. Once that's done, if you divide that by that parenthesis, we isolate dy dx. Okay? So let's do. Who wants to go for right-hand side here? What's in the right-hand side? No dy dx. Right. Yeah, I would 6y stays there and negative 3x squared. Thank you. That's one answer. Make sense? What's in the left-hand side? 3y squared. I'm keeping that guy over there. But this one's over here, so there's a negative 6x. Is that right? You see some common factor? 3 is a common factor. Let's get rid of that. So there's a y squared minus 2x. Is that better? And 3 is gone. Is a 2y minus x squared. This is the coefficient of dy dx, and right-hand side is just 2y minus x squared. What's the next step? Yeah, divide this one by the y squared. So dy dx is equal to 2y minus x squared. That was on the right-hand side. Left-hand side, this coefficient goes to the denominator. Make sense? So let's look at this formula. Dy dx, the derivative, is written not in terms of x, but interestingly enough, is mixture of y and x. Okay? So we don't know the formula of y, but there's x. And this is going to be useful when you calculate actual slope of a tangent line. Remember this notation? Dy dx, the derivative, and you plug in x equals a. Okay? Then, of course, all the x's become a there. Like that. What's going to happen to y? Here's a graph, local graph, remember? That was our point A. And that, when x equals a, there is y equals v. That's the xy relation for that implicitly defined function, correct? So whatever that y coordinate becomes this y in there. So 2b and b squared. So if you know one point, although you don't know the formula around it, this functional equation tells you the slope of a tangent line can be just calculated just knowing one point and the Cartesian equation, which is interpreted as a functional equation. Okay? So here is the formula. There is this thing given by x cubed plus y cubed equals 6xy, right? If I'm looking at a point, I discover this point, a comma b. Or if I give x coordinate 1 and you use a sage to calculate these 3 different points on there, right? So you can calculate y coordinate. Remember that part? So you have those points a comma b. How do you calculate slope of a tangent line there? What was the formula? If I have a comma b there, what's the slope of the tangent line if it's given by this Cartesian equation? 2b minus a squared divided by b squared minus 2a. That's the meaning of the value of a derivative. We just calculated here. Right? See what happened? That if you have that point, without knowing what the formula of this function actually is, we can use this Cartesian equation as a functional equation, and we were able to compute the slope. Clever, right? In it, there's a chain rule involved in there. Okay? And when you differentiate this functional equation, and these are important parts, so let's go through and practice one more time. So logically, it all derived, but I'm just laying it down for you. If you see y to the alpha in the implicitly defined function, what's the answer? Alpha, y to the alpha minus 1, right? Multiplied by dy dx. What rule is that? Chain rule. So what other functions are there that you will encounter? d dx of a sine y. Is that right? Maybe you're going to see that in the Cartesian equation. Then what do? Cosine y multiplied by dy dx. So I'm going to skip cosine and tangent, all right? What is the other thing? Maybe alpha to the y. Maybe you're going to see that in the Cartesian equation. And what happens if you differentiate this one? Interpreting y as a function of x. Anybody remember this? Alpha to the y appears again. This interesting thing about exponential function, and multiplied by ln first, right? Before we do, you complete that derivative first, and then multiply dy dx. All right. What's the last one? Log alpha y, right? Then you differentiate it with respect to y first. 1 over alpha, ln alpha. Is that right? Multiplied outside it here. Dy dx. Sorry about that. 1 over y, then ln alpha. So if you see this individual part, this is what you're going to do. Everywhere, just dy dx and dy dx appeared as a factor. Then you're going to collect all that, factor out all that, the same business. But you still have to be careful when you see something like this, x times the sine y, d dx. Then you have to apply the product rule first. Remember? Yeah. And then when you differentiate that part, and then you use this one. So for this type of thing shows up, and product rule first and sine y. When you differentiate the second part, second factor, that's where you use this chain rule in here. So I'm introducing this implicit differentiation as the application of what derivative rule? Chain rule. It seems like this is the application of a chain rule. What is the problem? There's a Cartesian equation, and we want to compute the slope of a tangent line there. That's what we're calculating here. Yes. Well, they have a list of examples that we're going to go through. But this is an example you did in homework in terms of just computing points. So that's that.